In electronics, a voltage divider is a passive linear circuit that produces an output voltage that is a fraction of its input voltage. Voltage division is the result of distributing the input voltage among the components of the divider. A simple example of a voltage divider is two resistors connected in series, with the input voltage applied across the resistor pair and the output voltage emerging from the connection between them. Resistive voltage dividers are commonly used to create reference voltages, or to reduce the magnitude of a voltage so it can be measured, and may also be used as signal attenuators at low frequencies. For direct current and relatively low frequencies, a voltage divider may be sufficiently accurate if made only of resistors, where frequency response over a wide range is required. A voltage divider may have capacitive elements added to compensate load capacitance. In electric power transmission, a capacitive voltage divider is used for measurement of high voltage. General case. A voltage divider reference to ground is created by connecting two electrical impedances in series, as shown in Figure 1. The input voltage is applied across the series impedances Z1 and Z2 and the output is the voltage across Z2. Z1 and Z2 may be composed of any combination of elements such as resistors, inductors and capacitors. If the current in the output wire is zero, then the relationship between the input voltage (VAN) and the output voltage (Vout) is. Proof. The transfer function of this circuit is. In general, this transfer function is a complex, rational function of frequency. Examples. Resistive divider. A resistive divider is the case where both impedances, Z1 and Z2, are purely resistive. Substituting Z1 equals R1 and Z2 equals R2 into the previous expression gives. If R1 equals R2, then if Vout equals 6V and VAN equals 9V, then, and by solving using algebra, R2 must be twice the value of R1. To solve for R1, to solve for R2, any ratio Vout/VAN greater than 1 is not possible. That is, using resistors alone it is not possible to either invert the voltage or increase Vout above VAN. Low-pass RC filter. Consider a divider consisting of a resistor and capacitor as shown in Figure 3. Comparing with the general case, we see Z1 equals R and Z2 as the impedance of the capacitor, given by where Xc is the reactance of the capacitor, C is the capacitance of the capacitor, J is the imaginary unit, and omega is the radian frequency of the input voltage. This divider will then have the voltage ratio. The product tau equals RC is called the time constant of the circuit. The ratio then depends on frequency, in this case decreasing as frequency increases. This circuit is, in fact, a basic low-pass filter. The ratio contains an imaginary number, and actually contains both the amplitude and phase shift information of the filter. To extract just the amplitude ratio, calculate the magnitude of the ratio, that is, inductive divider. Inductive dividers split AC input according to inductance. The above equation is for non-interacting inductors. Mutual inductance will alter the results. Inductive dividers split DC input according to the resistance of the elements as for the resistive divider above. Capacitive divider. Capacitive dividers do not pass DC input. For an AC input, a simple capacitive equation is: any leakage current in the capacitive elements requires use of the generalized expression with two impedances. By selection of parallel R and C elements in the proper proportions, the same division ratio can be maintained over a useful range of frequencies. This is the principle applied in compensated oscilloscope probes to increase measurement bandwidth. Loading effect. The output voltage of a voltage divider will vary according to the electric current it is supplying to its external electrical load. To obtain a sufficiently stable output voltage, the output current must either be stable or limited to an appropriately small percentage of the divider's input current. Load sensitivity can be decreased by reducing the impedance of the divider, though this increases the divider's quiescent input current and results in higher power consumption in the divider. Voltage regulators are often used in lieu of passive voltage dividers when it is necessary to accommodate high or fluctuating load currents. Applications: voltage dividers are used for adjusting the level of a signal, for bias of active devices in amplifiers, and for measurement of voltages. A Wheatstone bridge and a multimeter both include voltage dividers. A potentiometer is used as a variable voltage divider in the volume control of many radios. Sensor measurement voltage dividers can be used to allow a microcontroller to measure the resistance of a sensor. The sensor is wired in series with a known resistance to form a voltage divider, and a known voltage is applied across the divider. The microcontroller's analog-to-digital converter is connected to the center tap of the divider so that it can measure the tap voltage and, by using the measured voltage and the known resistance and voltage, compute the sensor resistance. High voltage measurement: a voltage divider can be used to scale down a very high voltage so that it can be measured by a voltmeter. The high voltage is applied across the divider, and the divider output, which has a lower voltage that is within the meter's input range, is measured by the meter. High voltage resistor divider probes designed specifically for this purpose can be used to measure voltages up to 100 kV. Special high-voltage resistors are used in such probes as they must be able to tolerate high input voltages and, to produce accurate results, must have matched temperature coefficients and very low voltage coefficients. Capacitive divider probes are typically used for voltages above 100 kV. As the heat caused by power losses in resistor divider probes at such high voltages could be excessive. Level shifting: a voltage divider can be used as a level shifter to safely interface different circuits which use different reference voltages. For example, an Arduino microcontroller works at 5V logic, while many sensors require 3.3V logic. Directly interfacing the Arduino with a 3.3V sensor may cause permanent damage to the sensor. By using a level shifter with a ratio of 3.35 resistor values on each pin connected to the sensor, an Arduino board can safely communicate with the sensor.